Hi, I'm Val, and I will be speaking about TMA operations, starting with the drone intrusions in TMA, an incident that happens more and more often these days, unfortunately. So here on the right, I have a representation of the TMA. So this rectangle represents a typical TMA. Actually, it's a schematic representation of the Stockholm TMA. So it has 4 entry points on each side and has a runway somewhere in the middle. And maybe it happens so that right here you have a drone spotting. So somebody saw a drone. Well, these black lines are the stars, and maybe the aircraft following your stars nicely, not affected by the drones. So why would you worry? Well, you worry because you don't know where the drone is, and it may happen so that in 5 minutes, the drone can be anywhere in this area. And if you have a good algorithm to modify your star so that it still avoids the drone affected area, then why don't you do that instead of closing the whole TMA? And in each of these pictures, I'm showing how the drone affected area may increase uh, based on the drone speed at every 5 minutes, and how the star can actually morph slightly to avoid the drone at every time. Of course, at certain times you may think that, well, maybe I will close this entry point because now the drones or the aircraft would have to fly around the affected area for too long. But still, maybe something like this, the morphing star, is a better fix than close the whole TMA just because you have seen a drone at some point. And in fact, my first poll question is exactly this. Do you think something like this, these morphing stars, or whatever you want to call them, could be a solution for mitigating the drone intrusion in TMA? Okay, so the drone intrusion is obviously a bad thing, but in general, drones and well, urban air mobility, the flying taxis are not a bad thing, and they do want to use the urban area, urban airspace. But if we look at pretty much any uh, urban airspace from the conventional aviation point of view, you will see, well, that a lot of this airspace is controlled and actually used by the stars and SIDS. So again, a quick solution is just to say, well, no drones in the urban airspace. That's probably not optimal. And what we are advocating for is to really look at what do you have as the obstacles for the drones. Well, they could be terrains and buildings. There could be procedures for the aircraft, other things. But still, maybe some airspace still remains free for UAM to fly in. And when thinking of such airspace, we want human input to decide on the different concept of operations and integration of the conventional aviation and the new entrants. And of course, we need computers to actually look at how the available airspace looks like. And here is an example of such a study that we did. So we identified quite a few possible obstacles for the drone operations and defined 4 integration concepts that I will go into some details. But in principle, any NSP can define their own concepts and do a study like this. So here are the pictures of the 4 concepts. The first one basically says, well, the UAM should just fly in the very low level airspace and nowhere else. We might also consider the full segregation when the UAM, the flying taxis, will be flying above the very low level airspace, uh, and the aircraft will fly along their procedures, but well, they will stay separated from the drone traffic. We could also think of a better integration when essentially both the drones, the small drones, and the urban air mobility can use any airspace, well, except of the SIDS and stars. And with a very futuristic, but hopefully working idea, we could think that, you know, the integration is so good that the drone operators and UAM operators know which procedure is actually in use, well, based on runway configuration, maybe some of the airports are just closed, and use any airspace except for the active airport procedures. So these are the four concepts of operations, and I will show you, well, a picture of how these how the available airspace may look like under all of the concepts. So I know there is too much on the single slide, but essentially in every column, we have the four different concepts, and in every row we have different um, altitudes. And in, you know, in a very low level, the terrain and the buildings, of course, play a role. Nobody wants to fly into a building. While as you go up, depending on the concept, different things are take up the airspace that could be potentially used by the drones. While, of course, if the drones are not allowed to fly in the controlled airspace, then as you go up, well, the typical TMA is this wedding cake turned over. Well, that takes up more and more space, airspace. The procedures take a lot of space. But if you go into more and more integrated ConOpses, then you can see that actually you may have some airspace left for the drones and UAM also at high altitudes. Okay, so just flashing back through the four concepts. Full integration, only don't fly through the active procedures, don't fly through the procedures, be fully segregated, or basically do business as now. Let me ask you the next question. Which of these four concepts, if any, do you think could be implementable? Of course, we also have to evaluate the risk. So when I was describing the concepts, I was thinking that, you know, the aircraft that really stay within their procedures and the drones stay where they have to stay, but the life is not really black and white. What happens is that the aircraft sometimes do go out of their procedures, and we have a pretty good understanding of how often they do it. So that translates to the risk of aircraft encounter. So here on the top right, I'm showing the actual trajectories, and probably you can recognize that some of the aircraft were vectored. And we can, by looking at the data, we can understand how often that happens. Still, to evaluate the risk for the urban air mobility from the vectoring, we have to ask the air traffic controllers and see how this vectoring was done. Was it a stressful thing? Then, well, you know, the controller requested to turn immediately because a conflict may happen. And if the controller also has to take care of an urban drone taxi during that time, then well, the risk is high. Otherwise, if the vectoring is more relaxed, then maybe the risk is lower. Surprise, surprise, the aircraft actually do not always stay within the controlled airspace. They do violate the boundaries. And good ANSPs, I know with good the ANSPs with good safety culture, they do the studies trying to understand how often that happens, and we can translate it into the again, air risks. And of course, the conflicts in very low level airspace, that's just completely separate work in the UTM. Okay, so let's forget about the drones and consider just the regular operations for the conventional aviation. A recent thing that came in and had a lot of promise in terms of being environmentally friendly and good otherwise is the concept of continuous descent operation. So instead of the stepwise approach, you know, the aircraft really just slides. So I like to think about it as a slide with idle thrust, no speed brakes. Really good thing, but turns out it may decrease capacity and may be hard for the controllers. And I would like to see why that is so and mitigate the problems. And before we start, let's see how hard is CDO star design. So let's say you have, a single entry point, single runway, everything is good, you have a really good aircraft, it's the one and only aircraft. My question is, how many CDO trajectories do there exist for the aircraft to land from this entry point onto this runway? And well, this time it wasn't really a poll, it was a quiz. I knew the correct answer. The correct answer is the infinite number of trajectories. So indeed, if you give the aircraft distance to go, then there are many, many different ways for using these track miles and wiggling around and landing on the runway. And of course, the distance to go can also be different, and the aircraft can execute quite a few, essentially infinite number of CDO trajectories. Well, that's from one entry point. Same thing goes for the second entry point, the third entry point, and the fourth entry point. So altogether, you have this, 4 times infinite, the number of the trajectories, and you have to pick one, one ground track, if we're talking about the star, per entry, so that they, merge smoothly and nicely, and there is a good separation between merge points, and so on and so forth. Well, it is a challenge, but this is possible to do. I mean, the procedures are being designed, and well, you can draw things like this. The real challenge comes in if you want to actually use this star to serve the demand. So you, at every entry point, you have these aircraft arriving at, well, essentially irregular intervals, or maybe even regular intervals, and each of them should just follow the corresponding path to the runway, no vectoring, really just sliding through. And well, of course, you can do this. You can say, well, these guys, you just go into a hold. I will just route the aircraft from the south, and then maybe an aircraft from the west and north, and so on. But you probably don't want to move the aircraft into the holding pattern for too long. You really want to slide them through these stars as they arrive. And we actually can do it. Turns out we can do it, except we cannot use a single star for the full hour. So we were doing experiments for a single hour when we more or less knew when the aircraft would arrive. We have to use 2 merged trees. And here's the little animation which shows how we did that. So the aircraft arrive within the first half an hour. 10 aircraft go along this arrival tree. And when the second half an hour comes in, another tree becomes the star. Well, the aircraft that are still in the air finish landing, but the new aircraft, and there are 7 of them, they use the second tree. So with using these 2 trees, we were able to put in 17 arrivals, all on CDO trajectories. That's considered medium density traffic. So yes, CDOs do reduce the capacity. And while we compared the trajectories to the CDO trajectories to the actual trajectories of these aircraft that they flew in reality, well, you can see the vectoring. And in fact, we have a separate project when we are talking to the to LFV and asking, well, why did you have to vector? Why your trajectories are not so optimal? But that's a separate story. Let's continue with CDO. We haven't solved all the problems. We haven't solved the capacity problem. So again, here is our concept for the trajectories. We're choosing 1 trajectory per entry point. Of course, we are doing it with the computer because that may be too complicated a task for a human controller. So we can go 1 step further. So I was talking about, yes, we can delay the entry of the aircraft to the TMA, but by how much should we delay it in order to land all the aircraft with CDO trajectories? Of course, we can tell, 1 aircraft per hour, and it goes along CDO trajectory. But turns out that if you allow to change the entry by plus or minus 5 minutes, you can get as many as 30 aircraft flying by CDO. And well, for Stockholm Arlanda, that's a high traffic scenario. And yeah, so actually we don't have to deviate the entry time by too much. And now I'm going into final part of my talks, talking about KPIs. Well, one KPI is that with our trajectories, aircraft spend less time in the TMA. So here are the actual ones, here are our trajectories. And here how they look. The blue ones are the CDOs, surprise, surprise, and the orange ones are the actual trajectories. And here on the right, I'm showing the fuel burned. You can see that, well, the actual trajectories burn more fuel than they would have burned if they followed the CDOs. Okay, so the last topic is KPIs. And one quick note that I want to make is that it's quite normal to set the development goals with respect to the forecasted traffic, right? In the future, in 5 or 10 or whatever years, you want to, increase capacity, keep the same safety, decrease fuel burn or environmental effect, and so on. So you're setting these goals, and then guess what? The future is different from your forecast. So some of the KPIs, they're just attained for free and much better than what you said. And some targets, they just become infeasible to reach. This was a serious issue when the European Court of Auditors was evaluating CESAR. So what we will wanted to look at is to see how with the decrease of the traffic this year impacted the KPIs at Arlanda. And here are the few results. Well, this is the number of arrivals. So the red is 2020. You see that the number of arrivals get down in March, May. The average time in TMA did go down, yes. So the congestion is smaller, so they probably spend less time in TMA. So this average time flown level is more or less how far from CDOs the trajectories were. Well, I don't know. You tell me whether the red is lower than blue or not, but at least not consistently. So here how the trajectories look like. Again, the red are the actual, and of course the red are the CDOs, and the black are the actual trajectories. So we looked at 2 days with 16 and 23 aircraft over the whole day. And you can see some trajectories are, well, quite far from being CDOs. And finally, we estimated the fuel burn. And well, the actual trajectories burn more fuel than they could have done if they were following the CDO trajectories on both days. And in fact, some of these extra fuel burn numbers are outstanding. So for this one, we really went down and took the flights and looked what happened. And it looks like that the runway configuration, well, they were supposed to land on one runway, they had to land on the other runway. We saw that there was a weather event during that time. So maybe that explains why the KPI is so bad. Okay, so this is the summary what we talked about, and I want to finish with the slide where I mentioned the work on which it is based, and thank our collaborators, and also thank you for your attention.